talk. So we're very happy to have our next speaker, Emmanuella Sandratra Rambeloson. I hope I got that right. And she'll be speaking about Schur-positivity of some trees.
All right. First of all, I would like to thank the organizers. I'm very excited to be one of the speakers here, and also I'm very happy to talk about my joint work with Professor John Sharishan. All right. Here is the plan of this talk. First of all, we are going to define what is Schur function. After that, we are going to define what is a chromatic symmetric function, and then we are going to talk about the Schur-positivity of some chromatic symmetric functions. All right. Let us define what is symmetric functions first. If we take x, an infinite set of variables, and n, a non-negative integer, a symmetric function of degree n over the rational numbers q is a formal power series like this one, where J here is the set of all with compositions of n, which means that J is the set of all lambda, such that lambda is a sequence of non-negative integers, and the sum of all lambda I must be n. Q lambda here is a rational number. X lambda is the monomial defined by lambda, which means that x lambda is x1 lambda 1, x2 lambda 2, and so on, where lambda is a weak composition of n. And if we take sigma, a permutation of positive integers, then we must have this equality here, that f of x sigma 1, x sigma 2, and so on must be equal to f of x1, x2, and so on. Now, we write by this notation here the space of all symmetric functions of degree n, which is a Q vector space. Now we're going to define what is Schur functions, but before that, I think we need to understand these little definitions here. If we take a positive integer n, a partition of n is a sequence of positive integers lambda, such that we must have these inequalities here, that lambda 1 must be larger than lambda 2, and so 1 must be larger than lambda p. And the sum of lambda I must be n. All lambda I here are known as parts of lambda, and this p here is the length of lambda, which is actually the number of the parts of lambda. Now, if we take lambda, a partition, we say that this area T of positive integers is of shape lambda if the number of rows of T is length of lambda, and if the number of columns of T per each row I is lambda I, which means that the number of columns of T differs per each row I. Now, if we take an area T of positive integers of shape lambda, and if we suppose that the rows of T are weakly increasing and the columns of T are strictly increasing, then we say that T is a semi-standard Young tableau of shape lambda, or T is a SSYT of shape lambda. All right, now let's see an example of SSYT. If we take this lambda here, which is a 75332, which is actually a partition of 20, then this is the form of an area of shape lambda where these entries here must be different than 0. And here is an example of SSYT of shape lambda. Here we can see very well that the rows of this area are weakly increasing, while the columns are strictly increasing. Now, if we take an area T, which is SSYT, the type of T is a sequence alpha, such that alpha I is the number of parts that equals to I in T. Alpha I is the number of parts in T that equals to I. All right, let's see this example here. For this SSYT of shape 75332 here, this alpha here is the type of it, where 0 here is the number of parts that equals to 1 here, 2 number of parts that equals to 2 here, 2 number of parts that equals to 3 here, and so on. That is the definition of type of SSYT. And now we're going to define what is a Schur functions. If we take a positive integer n and lambda a partition of n, then the Schur function of shape lambda or a Schur function of degree n is this formal power series here. This is the Schur function of shape lambda or a Schur function of degree n, where T alpha here is a SSYT of shape lambda. Alpha is the type of this T alpha here, and X alpha is the monomial defined by alpha. Now we can see in Stanley's book in chapter 7 that a Schur function is a symmetric function. And a Schur function of degree n is a symmetric function of degree n. We can see also in the same book that the set of all Schur functions of degree n form a basis of this vector space here. Remember, this vector space here is the space of all symmetric functions of degree n. Now we are going to define what is chromatic symmetric function, which was introduced by Stanley. If we take a finite simple graph J, where V here is the set of all vertices of J, E is the set of all edges, a proper coloring of J is a function K from V to the positive integers, such that if Vi and Vg is an edge of J, then we must have this, that Kvi must be different than Kvg, which means that the colors of Vi and Vg must be different. Now, the chromatic function of J is this sum here. This sum here is the sum of all monomials defined by all proper colorings of J, which means that the sum of xkv1, xkv2, and so on, xkvn, where n here is the number of vertices of J or the size of V, and k is a proper coloring of J. By using the definition of a symmetric function, a chromatic function, and also a proper coloring, we should see that the chromatic function of J is a symmetric function. And the degree of the symmetric function is this n here, the size of V, or the number of vertices of J. Now, we say that the chromatic symmetric function of J is Schur positive if when we write it as the linear combinations of Schur functions with the rational numbers, alpha s, we must have that all of alpha s must be non-negative. They must be non-negative. All right. Now we are going to talk about the main goal of this talk, which is actually to prove that this conjecture here is false. This is a conjecture of Dalberg, Schur, and van Willigenburg, which says that if we have an integer n larger than 2, then there must be a tree T on n vertices that contains a vertex of degree the floor of n to 2, such that the chromatic symmetric function of T is Schur positive. To understand it very well, let us see this example here. If we take n6, then among of the trees on 6 vertices, we have only this 3 trees here that satisfy the condition that we need here, which means that in these 3 trees, there must be a vertex that has degree the floor of n to 2, which is 3 here, since n is 6. For instance, in this tree here, this vertex here has a degree 3, and this vertex here also has degree 3. In this one, this vertex here has degree 3. All right, this conjecture here says that the chromatic symmetric function of one of these trees is Schur positive. And that is true, actually, since when we compute the chromatic symmetric functions of them, this is for this one, this for this one, and this for this one, then we can see here that this and this one are Schur positive. However, this one is not, since there is a negative coefficient here. All right, this conjecture is then true when n is 6. And I think, if I remember correctly, they have already tested this conjecture up to n is 19. However, they didn't continue also. Maybe it's because when n gets larger, then the number of trees that we need to compute on gets larger also. Or maybe also when we compute the chromatic symmetric function of a tree on Sage, then it's very expensive in terms of time complexity when the number of vertices is very large. However, in this talk, we are going to see that this conjecture is false when n is 20. But before that, I think we need to understand what is a stable partition of a graph, and also domination between partitions. A stable partition of a graph J is a set partition pi of V. Remember, V is the set of vertices of J, and pi then are partitions of V, such that pi I are independent in J, which means that there is no edge of J in pi I. If we suppose that the size of pi I is larger than the size of pi plus 1 for any I between 1 and k minus 1, where k here is the number of partitions pi I here. Clearly, we must have that this lambda here, which is the size of pi 1, size of pi 2, and so on, size of pi k, is a partition of the size of V. And we call that lambda is the type of pi. And now, if we take this mu here, a partition of the size of V, then we say that lambda dominates mu, or we write it like this: lambda dominates mu. If for any m between 1 and k, we must have these inequalities here. That is the sum of mu I must be less than the sum of lambda I when I is between 1 and m. And now I think we have enough backgrounds to understand the remaining of this talk, specifically to understand this lemma here, which says that if the chromatic symmetric function of a graph J is Schur positive, and if we suppose that J admits a stable partition of type lambda, then J must admit also a stable partition of type mu whenever lambda dominates mu. In consequence to this lemma here, we have this following result here, which says that if we have a tree on 2n vertices that contains a vertex of degree n, And in addition to that, if we assume that the chromatic symmetric function of T is Schur positive, then if we take X, a vertex of T, such that X is different than V, and also X is different than all neighbors of V, then X must be a leaf in T. All right, let us prove this. Since T is a tree, then remember a tree is connected. Then T has exactly one bipartition. And we note that bipartition of T by this pi here. Remember, in the corollary, we have this assumption here that there is a vertex V in T that has degree n. Then V and all of its neighbors must not be in the same partition, which means that suppose if I set V here in this partition pi 2 here, then all of its neighbors must be in pi 1 here. And now we should ask the question, where should we set the left vertices of T? Since we have n-1 left vertices, we don't know where to set them in pi 1 or in pi 2. If we suppose that this lambda here is the type of this partition pi here, stable partition pi here, then this lambda 1 here is the size of pi 1, lambda 2 is the size of pi 2. Actually, we don't know what is lambda 1 and lambda 2, but the thing we should know is that this lambda 1 is larger than n, and lambda 2 is larger than 1. And now if we take this mu here and n, a partition of 2n, then we must have this, that lambda dominates mu. Why? Since lambda 1 is larger than n. And now I claim that lambda and mu are similar. Why? Remember that we assume here that the chromatic symmetric function of T is Schur positive, and that the tree T admit a stable partition of type lambda. Then yeah, we can use this lemma here, which says that T must admit also a stable partition of type mu. Why? Since lambda dominates mu. More specifically, T admit a bipartition of type lambda, and T admit a bipartition of type mu. Then lambda and mu must be equal, since T has exactly one bipartition. Now we should set then all of these left vertices here in pi 2, since we have enough vertices in pi 1. And the degrees of these vertices must be at least 1. And suppose that one of them has more than one neighbors, for instance, this one, there must be a cycle here. And that's the reason why that these vertices here must be leaves in T. All right, and that is the end of this proof. Now, if we take a partition of nu of n-1, we can construct a tree T of up nu on 2n vertices like this one. One vertex V of the tree must have exactly n neighbors, and we name them by V1, V2, and so on, Vn. Remember, T here is the length of this partition here. T of these vertices are not leaves. T of them are not leaves, and T of these vertices have parts of up nu neighbors other than V. Parts of up nu neighbors other than V. All right, let's see this example to understand it very well. If we take n is 7, then we can then construct a tree T on 14 vertices by using a partition of 6. For instance, we take this partition 3 to 1 here. Then this is the tree arising from this partition. One vertex of this tree must have exactly 7 neighbors. this vertex 0 here has 7 neighbors. And 3 of the neighbors of this vertex 0 here are not leaves. Why 3? Since the length of this is 3. 3 of them must have parts of new neighbors other than 0. For instance, this one has 3 neighbors other than 0. This one has 2 neighbors other than 0. And this one has 1 neighbor other than 0. All right. In consequence to the corollary that we have just seen before, we have this following corollary, which says that if we have a treaty on 2n vertices that contains a vertex of degree n, and if we suppose that the chromatic symmetric function of T is Schur-positive, then there must be a partition up nu of n minus 1 such that T is isomorphic with T of up nu. This is the tree arising from the partition of up nu. This corollary here means also that if we have a treaty on 2n vertices that contains a vertex of degree n, then the chromatic symmetric function of T is not Schur-positive if T is not isomorphic with one of the trees arising from the partitions of n minus 1. Then because of this corollary, we can then reduce the number of trees that we need to check on, since if T is not isomorphic with one of these trees, then immediately the chromatic symmetric function of T is not Schur-positive. Of course, when n gets larger, then the number of partitions of n also gets larger, but at least we can reduce the number of trees that we need to check. And specifically, if n minus 1 here is 9, then we have 29 trees to compute. And I think we can compute them very well. However, we may need to wait 30 minutes to compute all of them. And now we have this following proposition here that if up nu is a partition of 9, then the chromatic symmetric function of the tree arising from arising from up nu is not Schur-positive, which means also that all of the chromatic symmetric functions of the trees arising from the partitions of 9 are not Schur-positive. And this also means that if T is a tree on 20 vertices, which contains a vertex of degree 10, then the chromatic symmetric function of T is not Schur-positive. And that's the reason why that this conjecture of Dalberg, Shi, and van Willigenberg here is false, since actually we cannot find a tree on 20 vertices that contains a vertex of degree 10 such that its chromatic symmetric function is Schur-positive. And now we may ask that, can we find a tree T with a vertex of degree 10 such that its chromatic symmetric function is Schur-positive? Then if the number of vertices of T is 20, then we have seen that we cannot find such a T. However, when the number of vertices of T is 21, that this is yes, which means that we can find a tree T on 21 vertices with a vertex of degree 10 such that the chromatic symmetric function of T is Schur-positive. And in more general, we may ask, can we find a tree T with a vertex of degree k such that its chromatic symmetric function is Schur-positive? K here is larger than 3. Then in our opinion, this also is yes. However, this is still an open question. All right, I think that's all. Thank you very much for listening.
Thank you, Emmanuella. Let's give her a round of applause. Are there questions from the audience? So I had a question, actually, if I could start. So right at the end there, when you said, okay, there is a tree with at least a vertex of degree 10, but it needed 21 vertices, right? That is Schur positive. So in the other direction, is there a tree of size 20, but maybe has a vertex of degree at most 9? Its vertices are degree at most 9 or something that is Schur positive as well. Like maybe the bound is just a little lower than floor of n over 2. Have you looked for such a tree, or do you think it might exist?
A tree on 10 vertices?
No, on 20 vertices, but you don't need the vertex of degree 10. Maybe you need only a vertex of, maybe if you had a vertex of degree 9, but no larger or something like that. Do you think there might be such a tree whose chromatic symmetric polynomial is Schur positive?
Maybe.
Like fixing the degree instead of fixing fixing the size instead of fixing the degree is my question.
Maybe, but I haven't thought about it.
Cool. Are there other questions?
I have a quick question. I was wondering if there are any like constructions that, given a tree that is Schur positive, creates new trees from it, larger trees that are also Schur positive.
That is maybe a good idea, but I don't know. I don't know for now.
Okay, let me do one more round if there's any more questions. It looks like Jim unmuted. Do you have a question?
I did unmute, but I don't have a question.
Oh, sorry.
I just unmuted to clap.
Got it. Okay, well then let's clap again. So thank you, Emmanuella.